Yes, any other question? So I just wanted to know what happens to those guys who has poor internet connection. Are they getting anything out of these things, or they are
So the
just left out?
default is calling back like people with poor internet connection, and like if some people face moderate difficulties, they generally look into the recordings or lecture notes and all.
Okay, okay. So I mean, recordings in YouTube's are good. Also, sorry, I did I send the link? I again forgot maybe. So I'm uploading. Oh, I did, right. Did I send the link? Upload the link? I think.
Yes, sir, it's on relearned.
Okay, in the VLAN, yeah, okay, yeah. So uploading YouTube is seems should do a little bit better for those who have less poor internet connection.
Yes, sir, it helps.
Okay, so other people can help them as much as possible, and they can approach me as well if they need anything, and you can make a WhatsApp group as well, whole of you, along with the two tutors and myself. And I mean, people can ask question there as well. All right. So if it is fine with you.
Yes, sir.
All right. So yeah, any other questions about last theorem? Right. So which is still in the blackboard. Do you have any question?
Sir, the
Yes.
Kn should be, I mean, Kn plus 1 should be a proper subset of Kn. So you have written that step, right? So
Yes. Yes. Yes.
can you
Yes.
just like briefly explain as to, I kind of have an idea, but I cannot pinpoint as to why the step, why that step happens.
So
Can you
yeah.
explain?
So as far as I understand, so you're saying why this, right?
Yes, sir. Yes, sir.
Okay. So did I okay get an equal to? Hmm. Hmm.
Pointwise convergence of Fn. Right.
That is true if it's pointwise convergence. The question is whether, so question she asked is this.
Sir, Fn is greater than Fn plus 1.
Right.
So Gn is greater than Gn plus 1. So Gn plus 1 is greater than epsilon. Fn is
So
greater
our
than Fn.
question is whether this can become an equality.
Whether this can become?
Equality and all the k's might be same.
Yes, then also intersection Kn is not equal to 5. So it's okay. I mean, it is trivially okay.
Of course, this is okay. This is true. That is there is no problem in that. But true, that is true. That is true. So this one is actually not a proper subset. So Kn is this one. So Gnx greater or equal to epsilon implies gn plus 1 x or other way. Right? Why? Let me see. Yeah, if I done this one, little bit of change or what? So Fn is decreasing, so Fn x is greater or equal to n plus 1 x. So this implies Fn x minus fx is greater or equal to n plus 1 x minus fx. All right. Right. Now, this one, if this is greater or equal to epsilon, then this is greater or equal to epsilon. All right. So this is fine. So Kn is a subset of, or Kn contains Kn plus 1. This is fine. So, I mean, do you have problems with this notation that this means proper subset? Does that your understanding, Nivedha?
Yes, sir. I have a little bit of a problem with that. That's it.
Oh no, this is not proper. So you will see later on this equality part of this part people omit in the recent literature. So whenever it is not equal, strictly not equal, then people write like this. All right, but in this case it is not. It's just a subset.
Okay.
Just a subset. So it is, and for this compactness theorem, you don't need to be proper one. Right? So it says whenever there is finite intersection property, intersection of finitely many is non-empty, implies intersection of all of them is non-empty. All right?
Yes, sir.
So does this answer your question? Yeah. So this is not proper. This is not proper. Not proper anybody. Proper. Superset. It's just a superset. All right. Now, how do you think? So this is compactness. Some theorems of compactness gives you a nice property, right? Isn't it interesting? Do you feel delighted understanding this, or using some theorems from last semester and getting pointwise from uniform from pointwise convergence to uniform? Yeah. Yeah, okay. So let us check now assumptions a little bit. We put compact set. Is it necessary? See, we used a lot of things, right, about compact sets. So what do you think? Compactness should be necessary, or at least you cannot go to the proof if you remove compactness? Right, so can you remove compactness? The question is, question is, can we remove compactness assumption? Yeah,
No, sir.
I cannot remove. Why?
Sir, because there, so I think 1 upon nx plus 1, uh, it will be monotonically, it will have monotonic character in, say, 0, comma 1, 0 open, 1 open, but it will not have a uniform convergence, I think.
Okay, so your name is Ayush, right? Yeah, you gave an example, which is counter example, which is fnx equal to 1 over 1 plus nx, and x belongs to where? 0, 1, open, right?
Yes, sir, 0, 1, both open.
So there is no compactness here. Right now, what happens?
Yes, sir.
Now, what happens? This one?
So it is basically monotonically increasing in this, but
No,
it
monotonically increasing. Fn plus nx is less or equal to fnx, and this is what we need for all x in 0, 1, right?
yes.
And it is pointwise convergence also. All right. So fnx converges to 0 as n tends to infinity. Right? Pointwise. So here it means fnx, when I evaluated something, so this means pointwise. So otherwise I will say fn converges to 0 uniformly or something. Fn converges to 0 pointwise, it means fnx converges to 0 for each x. Alright.
Sir, let's take the point 0 in the domain of in the definition of the domain. 0 close, open 1.
Okay. 0 close
Now
open 1.
pointwise converges to fx, where fx is 0 when x lies in 0, comma 1 open, and fx is 1 when x equal to 0.
Mm-hmm.
So
Right.
so that's not uniform, and that completes the counter example that we want.
No, here f is continuous also. So the limit function is continuous. So this is fine. This is fine. It converges pointwise, but does it converge uniformly?
It doesn't, because if you look at fn of 1 by n, you get half, and you cannot make that go to 0.
Fn of 1 by n is
Half.
right.
So say you found a capital N, you could always put x is equal to 1 by capital N, which is in that interval.
Then what happens?
So if you find a capital N for which given an epsilon greater than 0, and for all small n greater than capital N, you want fn of
Right,
less than
right.
epsilon.
So what is your name? Satik.
Yes.
Okay, yeah. Satik has a nice idea. So suppose fn converges uniformly to 0. Then what happens? For every epsilon, there exists a knot such that mod of fn x is less than epsilon for all n bigger than n naught and for all n x in 0 1. Right? So choose for every epsilon this is true, choose epsilon to be 1 over 10. Right? You better know for 1 over 10. Right? Now so choose epsilon, so we get an n naught such that star holds with the epsilon with epsilon equal to 1 over 10. Right? Now f of n naught plus 1 of 1 over n naught plus 1. What is this? What is the value of this? So fn is
1 by 2.
this is 1 over 2, right? Yeah, so 1 over 1 plus nx. So here n naught plus 1 times 1 over n naught plus 1. So half, which is bigger than 1 over 2. This is a contradiction. So this implies fn does not converge uniformly. Is this clear to everybody?
Sir,
Yes.
I didn't get like where do we use the compactness argument in this case? I mean, this could be proved without using the compactness argument also.
This could be proved. Which one could be proved? The theorem?
No, the example that 1 over 1 plus nx is not uniformly convergent.
No, this converges 1 over n. This sequence converges to 0. And 0 is outside.
Okay.
Outside the set. If you incorporate 0 and assume this to be continuous function, the limit, then you will get uniform convergence.
Okay.
There we are using. There we are using actually. You will not find these kns. I mean, using this example. So this will be a good experiment to do. So try to find this kns using these examples and see what happens. And whether this kn will be compact again or not. So this will be a nice experiment to do. Yeah, all right. Any other question here? Yeah, you might ask, what about other assumptions like decreasing, right? Whether you can remove that. Yeah. So those are not as decreasing point. Decreasingness is not a necessary condition. So you will get sequence. So this is an exercise. Let me explain now. Find a sequence of non-decreasing sequence of functions which is not decreasing but uniformly converging. I'm sure this is easy to find. And if you think a little bit for some time, you will find it. So is this clear till now?
Yes, sir.
All right. So the point is, so I'm going to state another fact, which we might come later as a proof. But let me to complete this this concern about whether pointwise plus what condition implies uniform. In this regard, I should make that comment. As stating that fact, which we might come at the end of the course, though it is not in the syllabus. So there is some property which is called equicontinuity. So this is out of syllabus, but just to mention, it will be interesting for sequence. I'm giving this definition. It is true for general family. So a sequence of functions on a set E functions Fn on a set E is said to be equicontinuous if for every epsilon there exists a delta greater than 0 such that mod of fnx mod of x minus y less than delta implies mod of fnx minus fny less than epsilon for all n in n. Do you see what extra assumption apart from this uniform continuity I have put?
So you have generalized the capital N and said it is for all for L for natural all natural number it is less than epsilon.
So
If
this
x
delta
minus y is
now does not depend on the function. This delta now does not depend on the function. It works for every function in that sequence, right?
Yes, sir.
Yeah. So that is why it is called equicontinuity.
So, sir, is this the same as saying that every function in the sequence is uniformly continuous?
Of course, it is stronger than uniform continuity. It is stronger than uniform continuity. So the same data works for every function.
It's not that each function is individually uniformly
It's
continuous.
even more. The same delta works for everybody. You know, this is a little bit technical stuff. And it is useful in the study of compactness of class of functions on a compact set. Right? So you know this in R, what are compact sets? Those are closed and bounded sets, right? Now if you look at all continuous functions on an interval, closed interval 0, 1, what are the compact sets there? You will learn this later. Those who will take up maths and go into the third year, I think in topology course. But I'm giving a glimpse of that here. This is the concept. Equicontinuity is the important point here. So why I'm giving this definition? Because of the following fact. Bounded sequence, bounded, pointwise, convergent sequence plus equicontinuity gives uniform convergence. This is clear. I mean, of course, this is not clear. It needs a proof, which we might come back later if we have time. But the point is, so we don't need decreasingness. What we need is certain things, general thing, like equicontinuity. You can check decreasingness up to certain stage. This, well, of course, this is a little bit distinct, but you can check whether this gives you equicontinuity. This might be a good exercise to check. Is this clear? Of course, we want to go beyond this one at this point. Of course, yeah. One thing I wanted to say, not after this, is since this is for those who knows metric space. And this is also, I think, out of the syllabus. So some out of the syllabus stuff will come here and there. So suppose if you consider class of all continuous functions, closed interval 0, right? Right? This is all continuous functions on 0, 1, right? And convergence here is uniform convergence. So Fn subset of this is 0, 1. Fn converges to F means Fn converges to F uniformly. And one can look at this one, supremum Fn x minus Fx x in 0, 1. This one can look at this, one can say Fn minus F, norm of Fn minus F, yeah, on 0, 1. Alright. So here Fn converges to F in this space means this uniformity. So what the fact is, what we get after doing uniform convergence, that C01 is a complete metric space. So in this case, Cauchy means Cauchy in this form. This in this norm. So norm of F here and norm of F01 is supremum over 01 mod of Fx. Alright, so this is a little bit of stuff out of syllabus, but what I'm just comparing with R, you get class of functions also from the complete metric space. Right? But you need a compact set. So it is in general true for any compact set. I put here 0, 1, but it is actually in general true for any compact set. Alright? So does this interest anybody?
Sir, I don't understand. Can you explain this part again?
Okay, so you consider class of functions on closed interval 0, 1, right? Now, in this case, closed interval 0, 1, what will be open sets? What will be closed sets? Right? So those things, those questions are there. And those questions are defined by, one can define using metric space. Right? And here, this one gives a metric. So V of Fg is supremum over 0, 1 mod of Fx minus Gx. This is the metric here. Alright? Now is this fine?
Yes, sir.
Yeah, so C01, you can consider a collection of all functions, all continuous functions on 0, 1 with this metric. Now this gives a metric space. If you have interest in mathematics, you can check that this gives a metric space. But now in this metric, Cauchy means what? Cauchy means uniformly Cauchy. What I was doing last time. Now uniformly Cauchy implies uniformly convergent, right? Now so this implies that any Cauchy sequence in this metric convergent. So therefore, this is a theorem which written in a different language, of course, but the basic is what we have done. Uniformly Cauchy implies uniform convergent. So we did not say anything new except the language of metric space in this case. So is this fine? Looks a bit heavy.
Yes, sir.
All right. So this is nice. Whatever we are doing using the uniformly Gaussian implies uniform convergence, it applies directly here. Class of functions. And you can change this to be to any compact sets here. No problem. The result holds. This is very interesting. All right. Now, if you have any questions, you can ask. We have 10 minutes, but yeah, 10 minutes. I'll start series, looking at series. But before that, if you have any question about sequence or functions, please.
Sir, the fact that any Cauchy sequence in this matrix space is uniformly Cauchy basically just stems from the definition of this matrix space, right? We define this matrix space, and it so happens that every Cauchy is uniformly Cauchy sequence. So, how does compactness play any compactness of this set play any sort of role?
Yeah. So the supremum will not exist, right? In general, if you don't take compactness.
Okay.
So this will not give a metric if you take if you remove compactness.
Sir,
Yes.
so suppose so the set we have taken that we take for defining the supremum, that is only bounded but not closed. So then can we say that then can we say that it's since the supremum will exist then?
Sir.
On open 01, 1 by x is continuous, but like supremum will not exist if you consider the constant function 0, say, and 1 by x on 01. No, I can't hear Zina. I'm just talking to Ayush.
Yeah, but like I understand, but like how does compactness ensure that there exists the function in that will be bounded?
Yeah. Any question? Yeah. Sorry.
The
That was
continuity on compactness will.
Compactness.
Okay. Niveda, ask your question again.
Yeah. I mean, if you have any, so if you don't take compact set here, continuous functions may not have supremum. So that is the reason compactness comes into the picture. Yeah, any other question? Yeah, any other question here? All right. So if we look at series, then what changes? Let us check. Just the definition today. So series of functions. So just like series of real number, we will consider series of functions, right? So you look at a series, formal series Fn, n belongs to n, like a formal series. We want to discuss the convergence or divergence of the series, right? So here there is some notions, right? So you look at Sn Snx to be summation j equal to 1 to n fnx fjx, right? Now you consider this sequence. So a series summation fn converges pointwise plus uniformly if the sequence of partial sums Sn, yeah, maybe small s, converges pointwise or uniformly. The corresponding statement will be true. If pointwise, if this you say pointwise converges, then this Sn converges pointwise. So a series converges uniformly if the sequence of partial sum converges uniformly. So maybe instead of slash, bracket is good. Yeah, it's better. All right. So the notion, along with this, what counts is absolute convergence. That is very important. Absolute convergence. A series of functions summation fn. So this n belongs to this some index number, some index a. So sequence of functions fn converges absolutely so on E, absolutely on E, a subset of R, if summation n from 1 to infinity mod fn x converges for every x to be. Is the definition clear? So this is what is little bit of distinctive than sequences. So here the convergence or divergence you can define using partial sums, right? Now sequence of real number or complex number, you had this, the same thing here as well. And there also you had absolute convergence, right? So a series, when it does not converge absolutely, you get whole set of real number, even extended real number as limit points, right? Right? Yeah. Riemann's rearrangement theorem.
Yes.
So that is the reason that there should, if you want a limit, if you want to define a function as the series, you rather consider absolute convergence. All right. So we want to define a function, define a series as a function, and we want to discuss properties like continuity, differentiability, integrability, stuff, right? All right. And for this is the right concept to take as convergence of series. All right. Okay.
No,
So,
sir.
yes.
So can you get over this last point once again?
So we'll discuss. So we want to define this to be a function, right? And then we want to discuss continuity, differentiability, integrability of that function, which can be written as a series. All right. Now, this one, if it does not converge absolutely, you will not get unique limit point. Right? For a fixed x, if you remove this one, then this number, of course, if you up to interchanging, you get different limits. This is what we don't want.
Okay, sir.
This is what we don't want. We want a limit. Of course, if you have one arrangement, you might get one limit, and you might discuss continuity or stuff like that. But this does not play a nice role with, interchanging this summation and differences in summation and limit. Those things become difficult if you don't assume absolute convergence. All right. So absolute convergence is the right concept here to go with. Okay, if you want to look at more about a series, sequence, and series of functions, and more than whatever the other books have, you can look at this book by Knopf, Sequence and Series of Functions, Sequence and Series, right? Or other infinite series by now. You can just browse through if you want. So this part is very important. So you want to look at, before going into differentiability, integrability, we want to look at this one. And these things we want to consider series as a function and want to look at continuity, differentiability, integrability of this one. And this is the most important points of this course. That when this series is continuous, differentiable, integrable, what would be the integration? What would be the derivative? Questions like that. All right. Okay. So we'll continue next day. If you have a question, you can ask. No? All right, then we'll see you next time.